To understand the concept of clustering, let's imagine a retail store. In such a store, we have customers with varying shopping behaviors and preferences. We might have early adopters. These are customers who are always looking to explore the latest products. We might have convenience seekers. These are customers who prioritize a quick and easy shopping experience. We might also have brand loyalists. These are customers who consistently buy products from their favorite brands. What else? We might have value seekers, customers who are always looking for the best possible deals. And impulse buyers. These are customers who make spontaneous purchases. Now, if you have all this information about your customers, you can do a lot of things with them. You can tailor your marketing strategies to each group's preferences, enhancing customer satisfaction and boosting sales. But we don't. One possible technique that automatically performs such customer segmentation is called clustering. What is clustering? Clustering is an unsupervised machine learning technique that is used to group similar data points into clusters. The goal here is to ensure that data points within a cluster are more similar to each other than those in other clusters. This helps in identifying patterns and structures in data which can be valuable for various applications. Before diving deeper, let's see, why do we need clustering from the first place? Often, we don't have labeled data. Data labeling is not only expensive and labor-intensive, but sometimes impossible to achieve. Clustering helps us understand our data by revealing underlying structures and patterns. This insight is crucial for making informed decisions and gaining deeper understanding of the data. Clustering can also help us identify anomalies and outliers, which are critical in areas like fraud detection, where unusual patterns need immediate attention. And finally, privacy preservation. By using clustering, we can enhance privacy by associating user data with cluster IDs rather than a specific user information. And most importantly, in some scenarios, labeled data can lose its meaning over time. For instance, in a music streaming service, users' taste evolves. A favorite song today may not be preferred tomorrow. Similarly, in a movie recommendation system, user preferences change and the labels can become outdated. Clustering helps adapt to these changes by dynamically grouping users based on their current behavior rather than just relying on their past behavior. Right, let's define cluster with this notation of centroid and spread. The location of its center and the characteristics of this spread. Now, one very important question would be, what makes a good clustering? And in order to answer that, let's look at a visual example. Let's say we have a bunch of data points here, and we want to apply two different methods to cluster them into 4 clusters. Now, you have 2 sets of results here, and let's visually look at this result and see which one makes more sense. None of them are perfect, that's for sure. But if you look at them closely, there are 2 areas that probably going to get your attention. So if you look at this area, you will see that the green cluster has much better internal cohesion in the right result than the left one. Also, if you look at the red cluster, you're going to see that the data point in the red clusters are very, very different from each other. On the right side, red is not perfect, but it's better than the left result. So that's just one thing. The other fact here is that if you look at the top left corner, what you see here is that the external separation between classes are just a little bit better in the right result again. So ideally, you want these 2 metrics, internal cohesion and external separation. So you want data points in a same cluster to be as similar, as close to each other as possible, and you want different clusters to be as different as possible from each other. Now, let's sum things up. In order to achieve a good clustering, you want to organize data into cluster such that there is high intra-cluster similarity, which refers to better association, data points in the same cluster being very similar to each other, and low intra-cluster similarity, which results in more distinct cluster and better external separation. A good clustering algorithm ensures both evaluate the quality of the clustering. We can use metrics like silhouette score, which provides a comprehensive evaluation of clusters' quality by effectively combining both intercluster similarity and intra-cluster similarity, measuring both compactness of within the cluster and separation between clusters into one single metric. Now, the formula looks like this, and what are A and B here? So A is the average distance to all other points within the same cluster, which is also referred to as intra-cluster distance, and B is the average distance to all points in the neighboring clusters. So in order to get a high silhouette score, you want your B to be as large as possible and your A to be as small as possible. Now, let's actually try to systematically and automatically group these data points into a bunch of clusters. In this case, 2 clusters. Now, where do we start? Okay, first thing first, if you had centroids, we could probably just start assigning the data points to the closest centroid, but we don't. Do we have the labels? If we had the labels, the cluster labels, then we could just measure the cluster centroid, but we don't have either of those. So how do we actually get started here? Where do we begin? So one way to go about this is making an assumption and then iteratively improve that assumption. Okay, so yeah, one approach to move forward here would be just randomly picking up 2 cluster centroid and get the ball rolling from there. Okay, so let's imagine these are my 2 cluster centroid. Now, what will be the next step? Well, I have 2 cluster centroid, but I don't have labels yet. It shouldn't be difficult now. What I'm going to do is I'm going to measure the distance between each of the data points here, each of the green ones, with respect to both cluster centroid, and I'm going to assign them to labels either blue or red, depends on which centroid is closer to that data point. Okay, if I do that, I'm going to get this clustering result. Now, you might just think, wait, something doesn't seem right. If you really look at this closely, the centroid actually do not represent their cluster. They don't seem to be the center of their cluster. And what I'm going to say here is, okay, let's actually do that right, make that right by taking an average of all the data points within the same cluster in terms of both X and Y, or X1, X2, based on different features that we have in this space. And then I'm going to fix that. It turns out we were right, actually, and the cluster centroid were not located correctly. Now, what you're seeing here is the updated centroids. Are we done? Maybe not. What you might be thinking is, whenever we update the centroid, we probably have to double check all the data points for possible reassignment. And you're absolutely right. So if we do that, we're going to get a slightly different assignment now. However, if we check, the current centroid are actually perfectly representing all the data points in their cluster. And if that means we are not going to move the centroid to any new location, and if we don't do that, we do not need any reassignment. So what happens here is that one step at a time, we improve the quality of the clustering. We started with random centroids, and then we try to make sense of the assignment, and then we had to go through this iterative process of updating the centroid and then assigning new labels to the data points multiple times. And then at some point, you will reach a final stage where no further update is needed. So what we actually described here is the idea behind a very popular clustering algorithm called K-means. Okay, this is how K-means algorithm work. We randomly initialize K centroids for K cluster, And how do we get K? That's actually an input to the system. That's a choice by design. Now, what we do afterward is that we're going to repeat 2 steps. Cluster assignment step, where we're going to look at which centroid makes more sense for each of the data points that we have. And then based on that new assignment, we're going to update the cluster centroids. We're going to keep repeating these 2 steps until we either happy with the result or no further updates can be made. Now let's watch a quick animation of k-means in action. Now let's take a look at the complexity of k-means algorithm. So let's define k as the number of clusters, n as the number of data points in the data set, d as the number of dimensions of each data point. So these are features that we're considering for this clustering problem. And finally, I is the number of iterations involved in order to reach convergence or until we terminate the algorithm. It turns out, in order to achieve or calculate all those distances between each of the 2 data points and across all different dimensions, we actually require a time complexity of big O, K, N, D, I. So it should not surprise you that if you have a lot of data points and your data is high dimensional, k-means can be very, very slow. One limitation of k-means algorithm that you should be aware of is that it can converge to local optima, meaning that the final clusters might depend on the initial placement of the centroid. So the initialization of the algorithm become extremely important in achieving high-quality clustering results. This can sometimes lead to suboptimal clustering results. So a local optima is a solution that is good, but not the absolute best. Okay, so let's see how this might actually impact the result. So I'll be showing you 2 different initialization on this data set. So this is the first one, and this will result to this final clustering result. And if, however, we had a different initialization, we could have ended up with this final outcome. So as we have seen, the standard k-means algorithm is sensitive to the initialization. Randomly selecting centroids can sometimes lead to suboptimal clustering because the algorithm can get stuck in local optima. K-means plus plus, a slightly different variant of k-means, tackles this challenge by employing a better initialization strategy. Let's see how this works. Let's say I have this data set to work with. So what I'm going to do, k-means plus plus starts by randomly choosing 1 data point as my first centroid. And then it will calculate for each of the remaining data points. We will calculate its distance to the nearest existing centroid. And then the next centroid will be selected based on a probability distribution proportional to the squared distances. This means that data points further away from the existing centroids have a higher chances of being selected. So probably in this case, the second centroid will be picked would be here. And based on this, we're going to update the distances and the probability distribution. And that might lead to our third choice being another data point that is as further apart as the previous choices. And we keep repeating these 2 steps until we have initialized all the centroids that we needed. So k-means plus plus algorithm improves the quality of the local minima and can lead to faster convergence. However, this benefits comes at the cost of having a more computationally expensive process at the beginning of the clustering. But wait a second, how do we actually choose the value of k? That's something we haven't talked about yet. And the value of k has to be decided at the beginning of the process. So if you look at this particular data here, most people would agree that this clustering result would seem ideal. However, this is not really clear-cut. So depends on the characteristics of the data and depends on the application or the purpose of the clustering. There are many different set of results that might still seem perfect or ideal. Okay, before introducing a method to calculate the optimum value of k, let's try to answer this question. Looking at the following graph, each graph shows how the intra-cluster distances changes as we increase the value of k or the number of clusters. Now, each of the following graphs shows how the average intra-cluster distances changes for each value of k. Feel free to pause here and think through this for a minute or so. Okay, what we really have here is that for each potential number of clusters k, if you run k-means algorithm and calculate sum of the square distances between data points in each cluster, what we're going to see is that because with higher number of clusters, you have higher chances of finding a closer or a tighter fit for the data points, we always going to reduce the intra-cluster distances. Or I can also say improving intra-cluster cohesion. And that will give us graph A. So when we increase the value of k, when we have more clusters, the odds are the data points in each cluster are more similar to each other. That's for sure. Okay, there is no correct answer here, but as we have seen, when you increase the value of k, the intra-cluster distances will decrease. Initially, this is going to be a huge reward. When you increase the value of k, you're going to get a lot of improvement in intra-cluster distances. But there's going to be a point where these differences kind of saturate and you're not getting much improvement for an increment in the value of k. So this is a technique that is called elbow method. And when you run k-means multiple times, you will find a sweet spot somewhere where that distances are saturating, and you're going to pick that as probably the most suitable value of k automatically for your data. Considering the very simple and intuitive nature of k-means algorithm, its performance is pretty amazing. However, there are cases in real world where a distance-based approach generally might struggle a lot because of the underlying assumption that clusters are always spherical and equally sized. In addition, clustering is not a clear-cut binary process or multi-class process. In real world, data points often exhibit characteristics that fall along a spectrum rather than fitting neatly into distinct categories. K-means also struggles with clusters of varying density, shape, and orientation. There are several other clustering algorithms designed to address some of these issues. GMM, or Gaussian Mixture Model, assume data is generated from a mixture of several Gaussian distributions. Not only there is flexibility in terms of size and orientation, but also we can perform self-clustering, which can help us with overlapping clusters. Hierarchical clustering is another approach that builds a tree of clusters. This can be very useful if you want to show relationship between your clusters. So there are many different approaches into clustering. Centroid-based or distance-based clustering was just one, and k-means was the most popular method in this category. Distribution-based clustering is another choice, and GMM, or Gaussian Mixture Model, is the most popular method under this category. We also have density-based clustering, and DBSCAN is a notable example. And we have hierarchical clustering, where agglomerative and divisive algorithms are two most popular models in that particular type of clustering. Thanks for watching. That's it for today. In the next videos, I will cover more clustering algorithms and machine learning concepts. Until next time, take care and stay well.